So the breakdown voltage of any insulation or flashover voltage of a gap. Okay. So at certain, we know the insulation is provided to the equipments of the power system to withstand the over voltages, surge voltages, or the traveling wave surges. Okay, so to overcome the fall means the faults. Okay, so if at certain over voltage means at certain over voltage the insulation breakdown of the equipment may occur. Okay, so or if any protective device is connected to the equipment, okay, if that such as lightning arrestor, in the lightning arrestor surge gaps will be there, and if over voltage occurs, then that over voltage may cause flashover at the gap. Okay, so the voltage across the gap during over voltage, we will call it as flashover over voltage or flashover voltage. Okay, so the breakdown of the voltage of any insulation or flashover voltage of a gap is a function of both the magnitude of the voltage and time of application of that particular voltage. Okay, so the volt time curve is a graph which gives the relation between the peak flashover voltage and time to flashover for a series of impulse applications of a given wave shape. So you know the impulse waveform or how the impulse waveform looks like. Okay, you can see here the lowermost curve. If you observe, you just observe the movement of my cursor. So this is the shape of the impulse waveform. Okay, and this is the peak of the impulse waveform. Okay, so if I want to break down the insulation of manually, if I want to break down the insulation of an equipment, okay, and if I want to plot the graph between voltage and time of application of that particular voltage. So if I want to, in order to break down the insulation of an equipment, definitely I have to allow some over voltage to flow through the insulation of the equipment. So whenever over voltage occurs, okay, so the magnitude of the over voltage, since I am applying over voltage to break down the insulation of an equipment, I can manually vary the voltage levels. So I will get different impulse waveforms of different peak values. Okay. So that's it. The volt time curve is a graph which shows the relation between the crest or means peak of the flashover voltage and the time to flashover for a series of impulse applications. So now to plot the time volt time curve, so we are going to apply some series, some n number of impulse waveforms of different peak values. Okay, so let us see how to plot this volt time curve. So this is the volt time curve. Let us see how to plot it. So here, what we are going to do is we are going to apply impulse waves of same shape. If you observe here in this graph, you can see all the impulse waves are of same shape. Of course, the upper waves are not completed; they are incomplete waves. Upper three waves, if you observe, okay. So the lower three waves, total six waves are there. Just for example, now to understand the concept. Okay, so total six waves are there here. Among six waves, three waves are complete impulse. They are looking like an impulse wave, but above three waves are not complete impulse waves. So our main aim is to understand the concept. So forget about whether these waves are complete or not. Okay, so these impulse waves are of same shape. All these waves are of same shape, and but they have different peak values. So peak value of this wave is this is this, and so on. If you see, okay. So the lowermost wave is the rated voltage of the system or the equipment which is to be protected. So rated withstand voltage means the of the insulation, I can say insulation of the equipment. Okay, so I means at this voltage the insulation breakdown does not occur. Okay, at the rated withstand value or at the rated withstand level of the voltage, the insulation breakdown does not occur. So the lowermost waveform impulse wave is the over voltage. When I give this over voltage to the for the insulation breakdown of the equipment, then the insulation breakdown will not occur for this lower voltage. Okay, so the main purpose of providing proper insulation to the equipments of the power system is to withstand against the lower voltages. So there will be a certain limit beyond which insulation breakdown occurs. So the withstand, there will be some withstand level of the insulation. So that withstand level voltage is this level. Okay, according to this graph. Okay, so this lowermost curve shows us that even though over voltage of this peak is given to the insulation of the equipment, insulation breakdown does not occur. So we can call that voltage at which insulation breakdown does not occur, we can call it as rated withstand voltage. Okay, and even though of course the insulation up to what voltage level the insulation can withstand is specified. Beyond that, okay, its withstand level we know now, this is the withstand level of the insulation of the equipment. And if the voltage level is further increased, okay, if the voltage level is further increased beyond its rating, then also if insulation breakdown does not occur, okay, beyond the rating of the insulation, okay, even though if insulation breakdown does not occur, then we will call it as critical withstand level. Okay, so at critical withstand level or at rated withstand level of the voltage, insulation breakdown of the equipment does not occur. Okay, that you people should remember. Okay, now in order to plot the volt time curve, okay, so here we are going to apply different wave shapes of different peak values in order to plot this volt time curve. Okay, so these are the over voltages which are applied on the insulation of the equipment which is protected. Okay, so if flashover occurs, if I apply some over voltage and if flashover occurs at the front of the wave, you know this, if this is the impulse wave, if this is the impulse wave, this is the front wave and this is the tail wave. You carefully observe the cursor. This is the tail wave, this is the front wave. Okay, so and before even reaching the peak value, if insulation breakdown occurs in the front, okay, then that point, that voltage at that instant where insulation breakdown occurs before even reaching the peak value is known as front flashover voltage. Okay, so here before reaching to the peak value itself, in the front itself flashover has occurred. Okay, so this point you will call it as this, the voltage at this point you will call it as front flashover voltage. Okay, so whenever flashover occurs on the front of the wave, the flashover point gives, this point will give a point to us to plot the volt time curve. Okay, so now do so at this point you can mention a point here. Okay, you can put a point here at this location wherever flashover has occurred. Okay, so the value of the voltage corresponding to this point is known as front flashover voltage. Now let us vary the voltage level. Let us okay, so if the voltage level is varied, okay, so if I'm reducing the voltage level, okay, to the insulation of the equipment, so when I reduce the voltage level, I have given some over voltage which is less than the previous over voltage value to the insulation of the equipment. If flashover occurs, you know what is meant by flashover. Okay, if insulation breakdown occurs, okay, if insulation breakdown occurs at the peak of the waveform, at the peak value, okay, suppose if you see the second curve from top, the second curve, if you observe at the peak, flashover has occurred, this particular point wherever I have put my cursor here. Okay, flashover has occurred at the peak value. Okay, then the voltage at that point you will call it as crest flashover voltage. Okay, voltage at that point you will call it as crest flashover voltage, and you just put a point at that point where our flashover has occurred. Now we have got 2 points at the front of the wave, you have got some point, at the crest of the wave you have got some point. Okay, now further I am reducing the over voltage to the over voltage that is applied to the equipment. Okay, and if flashover occurs in the tail region, okay, in the tail region, if you see the third wave in the tail region at this particular point, Okay, this is my third wave. Lower, I have reduced the voltage further, and the flashover has occurred in the tail region. The voltage at that particular point, you will call it as tail flashover. Okay, and further, if I reduce the voltage, okay, further if I reduce the voltage, and if the flashover occurs in the tail side of the wave at 50% of the application, means at the 50% of the peak value, we can say at the 50% of the peak value, and it fails to flash over in the remaining 50% of the application or in the tail value. Okay, so in the tail region, we can say, not even a value, in the tail region at 50% of the application, if flashover occurs. Okay, and so the voltage, actually you should not call, so okay, so if you will call the voltage at that particular point, you will call it as critical flashover. Okay, that point you will call it as critical flashover. Okay, and now you have got a point here, that is a critical flashover point, tail flashover point. Okay, and you have got a crest flashover point, you have got a front flashover point. So you have got some 1 2 3 4 points you have got. Now from the flashover points, draw vertical lines towards the x-axis. Okay, from the flashover point, from front flashover, draw a vertical line towards the x-axis. From crest flashover point, draw a vertical line towards the x-axis. From tail flashover, draw a vertical line towards the x-axis. And from critical flashover, draw a vertical line towards the x-axis, which is the time axis. And from the peak value of each waveform, of course, for a front flashover waveform, you will not get any peak value because flashover has occurred before reaching the peak value, so forget about it. From the second wave, from the peak value, draw a horizontal line. See, it is a horizontal line. Okay, from the peak value of next waveform, draw a horizontal line. So this is the tail flashover point. From there, you have drawn a vertical line. From the peak value, you have drawn a horizontal line. They will meet at a point here. Okay, they will meet at a point. For this crest flashover, already from the peak, you have drawn the vertical line. From the same point, you will draw the horizontal line. Okay, so no need to extend the line, vertical line here. You have to extend here. So when you go to 50% application critical flashover point, from the critical flashover point, already you have drawn a vertical line here. From the peak of the same waveform, draw a horizontal line. It will meet the vertical line at some point. This horizontal line will meet the vertical point at some point. That from that point, if you draw a line towards the y-axis, this is our actually critical flashover voltage. This is critical flashover point. This is critical flashover voltage. This peak value. Okay. So now these horizontal lines and vertical lines are meeting at some points, isn't it? So of course, for the first one, for our front flashover, you didn't get any meeting point for horizontal and vertical. Why? Because you can't draw the horizontal line because the flashover is not even occurring at the peak value. So forget about it. But you consider the flashover point. From there, move downwards, and it will meet the at the critical flashover point. Both the vertical line and horizontal lines are starting from the same point. So from here, join this. Okay, so from here, from the critical flashover point, move towards the tail flashover. Of course, from the tail flashover point, you have drawn a vertical line. From the peak of the same waveform, you have drawn a horizontal line. They both are meeting at some point. So join this dotted line up to this point. Okay, and let me check my luck. I will expand the screen. If the system cooperates. Okay, I have taken a pen so that I can draw. Okay, so that I can draw. Okay, so my luck is very good. My system screen is not expanding, so I'm going back and show. I'm going back. I have already expanded the screen, but it didn't expand. I'm going back to my previous screen. Okay. Okay, now. So this is my tail flashover. Now, from tail of course, this is not tail flashover point. From the tail flashover point, I have drawn a vertical line. From the crest of that waveform, I have drawn a horizontal line. They will both meet at this point. So I'm joining this dotted line up to here. Okay. I hope you all are carefully listening and looking at the screen. And as I move further, the critical from the critical flashover point, I have drawn a vertical line, and I have drawn the from the peak of the same waveform, I have drawn a horizontal line. They will meet at this point. So from here, from the front flashover point to this point, you will get a curve. Okay, this dotted line. This dotted line is nothing but our old time curve. Okay, this dotted line is the okay old time curve. So you already know the time range wavefront flashover. The time taken for the flashover of the voltage is the time range wavefront. Time range wave tail flashover, okay, up to here. Time range no impulse flashover beyond 50% of the application of the wave in the tail region. Flashover does not occur. Okay, beyond means at 50% of the peak value. Actually, if you want to determine the tail time taken for the flashover at the in the tail, you must consider the 50% of the peak value to determine the tail time, flashover time. Okay, so this is it. I hope you have understood. Still, a few more terms are to be discussed. Still, concept is not over. Okay, now so we are intersecting all these points here, and this dotted line is nothing but our volt time curve. Now, more voltages can occur due to lightning or due to switching operation or due to any LL or LG or LLG fault or LLL fault. Okay, the over voltage, it can be it can means it can be of any magnitude. We can't specifically mention the magnitude of the over voltage because it is a fault. Fault cannot be specified. Okay, if just for example, okay, just for example, let us assume that over voltage is up to 345, means based on the analysis, based on the study, what the engineers have found is that if the over voltage is up to 345 kilovolts, okay, the over voltage may be caused, means the over voltage magnitude is around up to 345 kilovolts, that over voltage may be caused due to system fault. Okay, fault within the system. Faults within the system are LL or LG or LLL, okay, or LLG fault. It can be any fault. Okay, so fault within the system or due to fault during switching operation. Okay, so and this if the over voltage has caused due to the faults due to switching operation or due to the fault within the system, and if the over voltage is around 345 kilovolts, means up to 300 and not beyond, it is below 345 or up to 345 kilovolts, then this over voltage may not damage the insulation of the equipment. Okay, insulation equipment insulation will not be damaged due to these faults. Okay, but it may damage the protective devices. Okay, so the over voltages which are around 345 kilovolts, okay, they may damage the protective devices instead of damaging the equipment because they are provided with proper insulation. Okay, now if the over voltage exceeds 345 kilovolts, okay, so if usually the over voltage will exceed 345 kilovolts if lightning surge occurs, if lightning occurs. Okay, so lightning can cause means can cause an over voltage of beyond 345 kilovolts. Okay, and these switching surges, means these over voltages due to switching surges, they are very dangerous than the lightning surges. Okay, so of course lightning surges are very dangerous. The over voltages that are caused due to lightning surges will be above 345 kilovolts only. Okay, and if switching surges occur due to lightning, then proper insulation coordination must be there for the protective equipment with respect to the insulation of the equipment to be protected. Okay, and this if over voltage exceeds 345 kilovolts, it will not only damage the protective device, it will also damage the equipment to be protected. Okay, so to assist the process of insulation coordination, okay, so between the insulation of the protective device and insulation of the equipment to be protected, standard insulations levels are recommended. Okay, so these, let us see those standard insulation levels according basic impulse insulation levels. Okay, so these are the basic impulse insulation level. These are the reference values for the equipments based on their ratings. Okay, this is the standard basic impulse level, and this is the reduced impulse level. Means the insulation should be a minimum of 450. For example, if the rating of the equipment is around 115 kilovolt, the insulation level should be around 450 to 550. So minimum insulation level required is 450 for the equipment whose reference value is around 115 kilovolts. Okay, so these are the reference values, these are the standard ones, and these are the reduced insulation level values. Okay, so these values, you I need, even if I tell about these values, you will not remember all these values, so you just go through it, that's all. Okay, so based on the rating of the equipment, as the rating of the equipment is varying, the insulation level, basic impulse level of the insulation as well as reduced insulation levels are also varying. Okay, so, so the basic impulse insulation levels are reference levels expressed in impulse crest voltage with a standard wave not longer than. So actually, how these basic impulse insulation levels are decided is considering an impulse waveform. Okay, if you are regularly attending my class, if you will remember, once I told you that I did my MTech project in CPRI Opal. So there is an impulse generator. So whatever the manufacturers will manufacture the transformer, they will provide proper insulation to the equipment, and they will bring it to the CPRI for insulation breakdown test. So insulation breakdown test is done in the impulse generator, which is available in CPRA. So they will keep the transformer which is provided with proper insulation within that impulse generator, and a standard impulse waveform of 1.2 microseconds to 50 milliseconds waveform is applied on that transformer. Okay, so what is this 1.2 microseconds and 50 milliseconds wave? 1.2 microseconds represents the front wave, the time taken, the time range wave front flashover, here it is mentioned, isn't it? So time taken to for the front wave to reach the peak value is the 1.2 microseconds. Okay, it will take around 1.2 microseconds, and the tail wave will have a time period of 50 milliseconds. Okay, it's not period, it's time. Okay, time interval of 50 milliseconds. The standard impulse waveform, front time and tail times are specified. So front time is 1.2 microsecond and tail time is 50 milliseconds. Okay, so of course, the apparatus insulation is tested based on the basic impulse insulation levels. Okay, so their insulation is decided. Okay, and suitable test is performed before bringing it to operation. Okay, so before means after manufacturing, immediately based on these impulse levels that have been provided here in this table. Okay, based on this insulation level, based on the rating, the standard impulse insulation levels are followed to provide proper insulation to the equipment. After providing proper insulation to the equipment based on basic impulse insulation level table, okay, it is tested. If it passes the test, then only it is brought into practice, means it is utilized. Okay, so that's it about the volt time curve. If anybody wants to ask, then you can ask me. You can unmute and you can ask me, or you can type R so that I will repeat the concept, or I will proceed to the next concept. You can type R if anybody wants me to repeat. So it's a simple and interesting concept. Okay, okay then. Next one is basic approach of insulation coordination. So you people are well familiar with the term insulation coordination if you are regularly attending my class. Okay, so the voltage withstand level of the insulation of the equipment which is to be protected, it is well coordinated with the protective level of the protective device such as lightning arrestor. For example, here I have written lightning arrestor.
Okay, so the protective level of lightning arrestor means what? Of course, its purpose is to protect the equipment against the faults. Purpose of using a lightning arrestor is to protect the equipment to whichever equipment it is connected, to protect it against the faults. But it itself has to protect itself if fault occurs. So a proper insulation must be given to the lightning arrestor. Okay. So when proper insulation is given to the lighting arrestor, first of all, if fault occurs, it has to protect itself. Okay, so that it will be able to protect the equipment later. Okay, now always whenever insulation is provided to both the equipments, means the equipment which is to be protected and the equipment which will protect. So equipment which is to be protected is it can be a transformer or generator or a motor. Equipment which protects is the lighting arrestor circuit breaker. Okay, it can be a lightning arrestor or circuit breaker. So till now we didn't discuss anything about circuit breakers. We have discussed only about lightning arrestors. So better we discuss about lightning arrestors. So or insulation voltage level. Insulation withstand level. Okay, voltage withstand level of the insulation of the protective device will be different from 1 minute. Okay. The rated voltage withstand level of the equipment insulation will have proper coordination with the protective level of the lightning arrestor, so that protective levels are lesser than the withstand level with certain protective margin. Okay, so that means that the insulation protective level of the protective device will be, my insulation level of the protective device will be less than the insulation level of the equipment which is to be protected. Why? Because if fault occurs, if over voltage occurs, protective device will be damaged first. Okay, if the protective device is unable to protect the equipment against the over voltage, then the protective device will be damaged so that the equipment will be protected. So always the voltage insulation withstand level, the voltage level of the insulation of the equipment will be always greater than the insulation withstand level of the protective device. Okay, this can be shown by some protective margin. Okay, so wait, I have to start the presentation. So this can be given by some protective margin. Protective margin is, you can write it as, it is the equipment withstand level minus protective level of the lightning arrestor is the protective margin. Okay. So always
Okay.
So there will always be a protective margin between the equipment and the Wait, I'll show you the presentation. I was disconnected once again because of the internet connectivity issue. Two times there was power discontinuity. Okay, so you can compare the voltage withstand level of the lightning arrestor with the withstand level of the uh, protective device in two terms, in terms of protective margin, in terms of protective ratio. Okay, so my presentation is not opening. I'm waiting for the presentation to open. We are about to complete this topic. I'll conclude this topic today. Okay, so wait, it's not opening. Yeah, it has. It seems it has opened. Yeah, I have to even join your class. I have not yet joined your class. Wait for a second. I'm about to present this screen. So earlier, when our Wi-Fi, so earlier, even if power cut was there, we had Wi-Fi facility. Now they have changed it. If power is gone, Wi-Fi is also gone. Otherwise, I might have taken class using my mobile. Okay, so even my mobile data is not working. Okay, so that's the reason. Otherwise, earlier I used to take the class even using my mobile data. I don't know what's the issue. Yeah. Okay. So I hope you are able to see the screen, and we didn't reach to the screen which I wanted to show. Yeah. So this is it. So protective margin is what? It is the equipment withstand level minus protective level of the lightning arrestor, and protective ratio is the impulse withstand level of the equipment by protective level of the lightning arrestor. Okay, impulse withstand level of the equipment by protective level of the lightning arrestor. So always remember that protective level of lightning arrestor will be less than the impulse withstand level of the equipment, so that if protective device is unable to protect the device or the equipment against fault, then it will get damaged. Okay, so you can see here, this is a tower with a transmission line. This is the line. This is a circuit breaker. This is the lighting arrestor. This is the equipment which is to be protected. Something I got it from the internet. Okay, so I had told you that equipment will have its own insulation. Okay, proper insulation will be provided to the equipment to withstand the over voltages. Okay, so you can see this is a transformer. Bushings are there. Okay, so and it is filled with the transformer oil. Voice is breaking. So wait. So this is the transformer. Okay. So here, if you can see, the transformer is connected. Lighting resistor is still voice is breaking. Voice is breaking still. Uh, maybe connected is there. Okay. Now is it okay? Is it okay now? Because we don't have enough time, we have to conclude this. Huh? Okay, you can see a lightning arrestor here. You can see surge arrestor and still breaking. Okay, So then I will not. I have downloaded some images from the internet. This is the transformer, and this is the transmission line in which lightning surge has occurred. You can see here a traveling wave is traveling through this transmission line. Okay. So if our voltage occurs, okay, if still it is breaking. I don't know why. I don't know why my voice is breaking. Okay. So um, so insulation coordination between transmission line and substation equipment. So if you see, we can coordinate the insulation bit of the transmission line with the substation equipment. We can coordinate them in two ways. Either line is over insulated or the substation is over insulated, we can consider. So I have considered the first case where the line is normally insulated and substation is over insulated. Okay, so this scheme is applicable whenever the overhead line is grounded. If we provide a, ground wire above the overhead line, are you able to follow because of voice break? Okay then, if my voice is breaking and if you are unable to, are you able to follow or not? You just tell me. If you are unable to follow, I'll continue in the next class. Do you want me to continue in the next class? Okay then, I will conclude and I will continue this in the next class. Okay. Okay, I will take attendance now. Okay, 201,
Yes, ma'am.
2,
Present, ma'am.
3,
Present, ma'am.
4,
Present, ma'am.
5,
Present, ma'am.
6,
Yes, ma'am.
7,
Yes, madam.
8,
Yes, ma'am.
9,
Present, ma'am.
10,
Present, ma'am.
11.
Present, ma'am.
1 minute, I have to stop recording.